All right, so again, 2-4, we talked about i's. We treat i's just like variables, like an x, with the exception of I squareds. I squareds are always going to replace, or I to the fourth, or anything like that. Anything over I to the first, we replace with what it would simplify to be. So for number 1, we're just going to take and distribute this. So I distribute the 9i into both the 5 and the negative 3i, and I get 45i minus 27i squared. That I squared becomes a negative 1, and negative 27 times negative 1 becomes positive 27. And then we write this in standard form, which means what? Good. The I always comes last, so this would be 27 plus 45i. You'll know it's in standard form if the I is the last thing that you've written. Raise your hand if you got that one right. Okay, good. All right, then moving to the next one. So this time I've got negatives underneath my roots. So the first thing I want to do is take those out. This would be I root 21 plus 3I root 45. And then as they are, I can't combine them because the roots are different, but I can use my factor tree to simplify this. So this would be 2 and 10 and 2 and 5. Each pair of 2's brings 1 to the front, so this would be 2I root 5. 45 would be 5 and 9, which is 3 and 3. Each pair, again, comes out to the front. There's already a 3 on the outside this time, so I multiply that together. And I would get 9i root 5, because there's only the 5 left underneath again. Now they both have an I and they both have a root 5, which means I can combine them. 11i root 5, which is 11 root 5i. So if this is an open-ended question, like your quiz is open-ended, I would actually take either of those answers. Just be really careful when you write it this way that you don't put the I underneath the root, okay? That would be wrong. It needs to come to the outside. And a standardized test usually has it the second way, where the I is the last. Esty.
When is the quiz?
Tuesday. All right, so 5 plus I over 5 minus I. Now I've got an I in the denominator, right? Can it stay there? No, so what do I do?
Conjugate.
Multiply both the top and the bottom by the conjugate. So 5 minus I and 5 plus I in both the top and the bottom. So I'm going to multiply out the numerator first, right? So 5 times 5 is 25. 5 times I, 5i. I times 5, 5i. And I times I squared. 25 plus 10i. This becomes a negative 1, so minus 1 is 24 plus 10i, and that's the numerator. With me so far? All right, then I want to do the denominator. So you can go through the process of multiplying that out, or you can use the shortcut. What's the shortcut?
A squared plus B squared.
Good. So what's my A?
I.
The 5, and what's my B?
I.
So there's the catch. The I is not the B. What's the B? The 1, okay? So be careful not to take the I with it, because on this one, it's just going to end up being negative 1, and then you would have A squared. It's plus B squared. You would end up subtracting it, which would be wrong. So you want to ignore the I and take what's on the front for the B. So this is 5 squared plus 1 squared, which is 25, plus 1, or 26. That's your denominator. And then I would split and reduce. So 24 over 26 plus 10 over 26i is 12 over 13 plus 5 over 13i. And again, standard form puts that I last. Who's 3 for 3? Okay, good. And then the last one, solve using quadratic, right? So this is not factorable. A would be 16, B would be negative 4, and C would be 3. S.
For the last one,
okay, so here I'm going to do negative b plus and minus the square root of b squared minus 4ac all over 2 times a. So b, negative 4 is 4, plus and minus the square root of negative 4 squared minus 4 times a, which is 16, times c, which is 3, all over 2 times a, which is 16. I get 4 plus and minus the square root of 16. Okay, this is 64 times 3 is 192. So minus 192. All over 32. Okay, the I is already out front. So then this is 4 plus and minus the square root of negative 172. No, 176, right? Yeah. Over 32. Oh, I don't need the negative underneath because the I will come to the outside. 4 plus and minus I root 176 over 32. 176 is 2, and 88, 2, and 44, 2, and 22, 2, and 11. 4 plus and minus I, this is 1 pair of 2's, 2 pairs of 2's, so 2 times 2 is 4. Root 11 over 32. 4 over 32, plus and minus 4 root 11 over 32. I'm going to kick the I to the outside. This becomes 1/8 plus root 11 over 8I. So got to keep going until you can't go any further on the simplification. Yep. So again, like on an open-ended question, as long as it's simplified, you could leave it, but the I's got to be, it just can't be underneath the root. Be careful not to put it under the root. But on a multiple choice test or standardized test, it's going to be split like that. So you need to make sure, because what would happen if you could simplify just half the fraction and not the other half? That would have to be split. So if you go, like if it was like 4 over plus or minus 6I, let's just say, root 11 over 30, I should do 36 because they both go into it, okay? But they go into them differently. So if I leave it, it becomes, I can just divide each of those by 2, right? That would be 2 plus and minus 3I root 11 over 18. But this fraction, that part of it can go further. In that case, it has to be split because you can simplify part of it more. So just be really careful. Questions on the warm-up? So the first thing I would do is take out the I. Oops, 240. And then use your factor tree. So this is 2 and 16, 2 and 8, 2 and 4, 2 and 2. Bring them out in pairs. So 1, 2, that's 2 pairs of 2's. 2 times 2 times I goes on the front, which is 4. I root 2. And then go to the 240. Break that one down. This is 2 and 120, 2 and 60, 2 and 30, 2 and 15, 3 and 5. And then again, pairs. So that's 1, 2, that's a second 2. And this time the 3 and the 5 would get grouped together. There's no match there. So this would be plus 4I root 15. And since those roots are not the same, you can't combine them. So in order, it should have been like 4 root 2I plus 4 root 15I. But then they don't break down.
I think, because I had the same problem when I implemented that and I did it wrong.
Okay. Remember, you can go back in after 8 a.m. and see the correct answer and see why, right? Yeah. So the fundamental. 2.5 is called the Fundamental Theorem of Algebra. Okay, it's a lot of the same stuff that we did in 2.3 with zeros and stuff like that, except that now we're going to have imaginary zeros in addition to our real and our rational zeros. Okay, so that's kind of the only thing that's getting added in. So you still have to pay attention to things like factors and roots and complete factorization and taking roots and finding the function from that, all that stuff. Using a graphing utility to verify, comparing X-intercepts, all that stuff is the same. The difference is now you've got imaginary roots combined in with your regular roots. So the linear factorization theorem says that if f of x is a polynomial of degree n, where n is greater than 0, then f of x has precisely n number of roots. In English, that means whatever the highest exponent is, the same number of roots you're going to get. So when you look at your function, you want to identify your highest exponent, that's your degree. Whatever that is how many roots you should get. Exactly that number. The difference is some of those roots now are imaginary. They still count as roots. So So here's just an example of all the different kinds of roots you can get. It says, be sure to you're familiar with the various kinds of zeros of a polynomial function. Here's a quick example. So if this polynomial was expanded out in linear factors, right, that's what that would be, and you looked at the individual parentheses and solved each one. So the first two, which are x plus 3 and 2x minus 1, when you solve those, you get negative 3 and 1/2. These are called rational zeros, okay? Rational number is a number that can be written as a quotient, so one number over the other. It's a decimal that either terminates or repeats, like 1/3, okay, or like 1/2 where it terminates, or a whole number. Those are rational zeros. When you get into your square roots, like here and here, these are called square roots of non-perfect squares. These are called irrational roots. So if I actually hit square root 2 in my calculator, you're going to see that number go to the edge of your screen. It doesn't end and it doesn't repeat. Those are irrational roots. Both irrational and rational are considered to be real zeros. So carefully look for the wording on problems. If it says identify the real zeros, then you're doing rational and irrational. If it now says give all the roots, now it's including your complex imaginary zeros. So these two would obviously result in something like this that has an I on it. These are imaginary numbers and these are the non-real zeros. So if your question now says find all the roots, you're including the non-real numbers. If it just said find all the real roots, then you're not including i's as part of your answer. Yes?
So real is rational or irrational?
Correct. Real is rational and irrational. So the good thing is like your test is separated out, right? Like we did the real zeros already. Now we're getting into both real and unreal. But if this is like a midterm question or a cumulative question and it just says find the real zeros, you're pretending like you're not even looking at, or you can look for the i's, but you would not give them as an answer. So be really careful. A standardized test might say give the real zeros. Those you would not include I, but the give all the zeros would include it. Does that make sense? Okay, so you got to really pay attention to the wording on things. So this one just says find the exact number of zeros. This should take you 10 seconds. Don't find the zeros. Tell me how many there would be. 3. Highest exponent. Easy question, right? Definitely not on a quiz or a test. But if you know that, then when you go to the next ones, which are actually finding the zeros, you should be able to look at your answer and say, okay, there's 3 there. I was supposed to have 3. Good, I have them all. If I'm supposed to have 3 and I only have 2, then I know something's wrong. So example 2 says solve the function. So if I look at A, the first thing I'm going to try to do is factor these. Can you factor x squared plus 36? Nope. So I'm going to solve it by setting it equal to 0. I can subtract the 36. I can square root both sides, making sure I do what on that left? Plus and minus. So this is plus and minus the square root of negative 36, which is what? 6i. So my answer would be negative 6i and positive 6i. There are 2 of them. If I look back at my question, the highest exponent was squared, which tells you I should have had 2. Okay, this time, can you factor to start? To start, yeah, right? We can do what? We could take out the x, yeah. And then x squared plus 25, that can't be factored. So I'd split it. I'd get 0 equals x. And I get 0 equals x squared plus 25. Negative 25 equals x squared. X would equal plus and minus the square root of 25, which is plus and of negative 25, which is plus and minus 5i. So my roots are negative 5i, 0, 5i. You can give them to me as plus and minus 5i. I don't care. That's fine. Just make sure that you know that that's 2. So when you count them, 1, 2, 3, 3 roots matches your highest exponent. Raise your hand if you got it right. Good. Questions so far? All right. Now it says find all the zeros of the function and write the polynomial as a product of linear factors. So what's a polynomial? What's a product of linear factors look like? So this is like one of those questions people ask me on the test. I say, I'm not telling you what that means, right? What does linear factors look like? What's the difference between zeros and linear factors?
That's a point.
X plus, wait.
Yeah. So the zeros are a list of what the x values are, right? X equals 1, 2, 3, 4, 5. Those are zeros or solutions or roots, all the same thing, right? Linear factors is x minus 1 times x minus 2 times x minus 3. Does that make sense? So you've got to know the terminology to know how to answer these questions. Say again. So the zeros themselves are your list of what x equals, like 1, 2, 3. Linear factors is x minus 1 times x minus 2 times x minus 3. So it goes behind the x minus. All right, so if I look at A, is this factorable? No, which means I have to do what? Good old quadratic, right? So A is 1, B is -3, and C is 1. So the opposite of B, which would be 3 plus and minus the square root of -3 squared minus 4 times A times C, all over 2 times A. 9 minus 4 over 2, root 5 over 2, which becomes 3 over 2 plus root 5 over 2, and 3 over 2 minus root 5 over 2. So those are the zeros or the roots. Solutions, okay, that's what those would be. Now to write it as a product of linear factors, I have to put x minus in front of each of those. So x minus 3 over 2 plus root 5 over 2 is going to get the parentheses because that minus is going to both. And then x minus 3 over 2 minus root 5 over 2. Anna.
I never remember, like, can you make those, like, fractions that you split into two, like, as one? Like,
We want them to be split back out and anyways.
okay.
So I'll show you, like at the end you want them to be split up anyway, so you're doing double the work.
Okay.
So now that minus goes to both, so -3 over 2 minus root 5 over 2, and then x minus 3 over 2 plus root 5 over 2. So we're close, but you can't have fractions within the parentheses. So what could I do to each set of those parentheses to get rid of the over 2's? Multiply by 2. So the 2 is going to go in the front here and the front here and get distributed into both set of parentheses, or each one. So this is going to go to all three, which means it's going to be 2x. The 2 on the bottom of the 3 is going to cancel out. The 2 on the bottom of the root 5 is going to cancel out. Same thing with the second set of parentheses. The 2 is going to get multiplied by the x, get canceled from the -3 halves, and get canceled from the positive 5, or root 5 halves.
Why can't you have a fraction in
It's just not, it's not written, that's not linear factor form. You can't have a squared because it wouldn't be a linear factor, and you can't have the fraction in them. So this is what it's looking for when it says product of linear factors. And if I had extra time and I wanted to FOIL that back out, I should get my question. I should get that x squared minus 3x plus 1. So know the difference between roots or solutions and product of linear factors. Here.
So linear factors can't have any exponents?
Correct. Yep. All right, you try B. So find. All right, so if you got to this point, right, so like I factored the first one, 4x squared plus 9, 4x squared minus 9, and then the 4x squared minus 9 can go further to 2x plus 3 and 2x minus 3. From there, those two roots, the ones on the right, were negative 3/2 and positive 3/2. The one on the left, I had to subtract the 9, divide by 4, square root putting the plus and minus, and I got the square root of negative 9 over 4, which becomes plus and minus 3i over 2. Those would be my roots. But then if it wants the linear factors, so if I had actually done x minus 3i over 2, x plus 3i over 2, x plus 3 over 2, and x minus 3 over 2. First of all, I could have saved myself some work on these because they are the same thing as these up here. So I can, God bless you, go straight to 2x plus 3 and 2x minus 3 there. And then all I have to do is multiply my first two parentheses by 2, and I get 2x minus 3i and 2x plus 3i. So God bless you. That's the product of linear factors with all four factors. And again, if you multiply that out, you should get your question. So now this one says, find all the possible zeros of the function, then find the actual roots, write the polynomial as a product of linear factors, use the factorization to determine the x-intercepts of the graph for the function, and then use a graphing utility to verify that the zeros are only x-intercepts. So we got to break this apart, right? The first part says find the possible zeros of the function. How do I do that? How do I find the possible zeros? No, that's the number of zeros, right? How do I find the actual possible ones? Last over first. So I'm doing plus and minus last over first. So first is just 1, right? But last is 1 and 16, 2 and 8, and then 4 and 4. So I would do plus and minus all the last over the first. This time it's easy. They're all going over 1. So it's 1, 2, 4, 8, and 16. Those are my possibles. That's the first part. Yeah, because 4 are the same possible root, right? We don't repeat possible roots. Then find the actual zeros. So what I could try to do is look at something and say, can I factor this? There's 5 terms there. I can't factor that by grouping, right? So if I can't factor it, what can I do? Do synthetic division until I find the one that works, right? Fun stuff. So I'm going to start with 1. I'm going to do 1 on the outside. Look at my coefficients. They're in order from highest degree down to none. I'm not missing anything. So 1, negative 4, 8, negative 16, and 16. Bring down the 1. One doesn't work. So I try negative 1. Doesn't work, so I try positive 2. And that's the first one that works. So I know that 2 is one of my zeros. I've reduced this a degree, so I've got 1 less than the 4th, which means this is x to the 3rd minus 2x squared plus 4x minus 8. And the first thing I would say is now there's 4 terms, so I should see if I could factor it by grouping. Can you take something out of the first set of parentheses?
Yes.
X squared. Can you take something out of the second set of parentheses? Positive 4. What's inside the parentheses is the same, so factoring by grouping worked. And I'm here with my remaining factors, and then I got to solve them. So I set this equal to 0, this equal to 0, x equals 2, negative 4, plus and minus the square root of negative 4, plus and minus 2i. So I already have 2, but this is telling you that there's another 2 as a root. And there's a 2i, and there's a negative 2i. So why would it be important that 2 is there twice? Think about it. There are 2 factors. I could have done a multiplicity of 2. That's fine too. But what's that going to affect? The graph. What's going to happen at the graph there? So it's going to bounce. Because I'm talking about a graph, I would definitely want to remember that that has a multiplicity of 2. But also because when I write the polynomial as a function of linear factors, if I only put 1x minus 2, it's wrong. I need both. Okay? So if you're listing the zeros and you just want to put 2, that's fine. I won't mark it wrong. That's technically correct. But you have to know that there is 2 2's so that when you go and do your x minus 2, x minus 2, x minus 2i, and x plus 2i, all 4 of them have to be accounted for. Does that make sense? Yeah? Okay. So the 2 2's came first from synthetic and then from factoring what was left. So now this says use the factorization to determine the x-intercepts of the graph of the function. So what do we think the x-intercepts are going to be? Just 2, right? 2, 0. Because will you see a 2i on your graph? Will you see a negative 2i on your graph? No. Okay? And then it says use the graphing utility to verify that the zeros are the only x-intercepts. So I graphed this. But I didn't. So my graph looked like this, which confirms what we thought was going to happen because there's only one x-intercept. It bounces at that intercept because it had a multiplicity of 2. Okay, the other real zeros will not show on your graph. So on homework, if it says use a graphing utility to verify, wait until you've done the problem to then graph it, okay? If this was a question on your test, you could actually do this without your graphing utility, right? Every part of that didn't need the graphing utility until I just went to confirm it. If it was the other way around, if this was on a portion of, which I haven't made yet, but let's say it's on the portion of your test that would require the graphing calculator, then you would do it similarly to the one you just did. You would have a function, you would then graph your function, find the one that's on your, compare it to your possible roots, right? List your possible roots, then graph your function, find the real root that's on your possible, that's on your graph and on your possible list to confirm that that's the root. Use synthetic division to reduce it a degree, and then either factor or solve what's left, but you should have imaginary roots at that point. So those roots would not be on this test, right? On the last test, you had roots, they were just not whole numbers, right? So that it crossed through your axis a couple of times. Those other roots were real numbers. They just weren't easy to identify because they were fractions that didn't terminate, which I picked purposely. But on a test like this, you would not even see the other roots because they're going to be imaginary. Questions so far?